Everyone, or afternoon, wherever you are. I believe you're welcome to the first online journal club of Afrimedphysics Hub. It's our intention and I hope that this meeting is going to serve as a platform to discuss recent scientific development in the field of medical physics, and also enable social interaction among participants and further areas in which we can look into for research. Today is the first one, obviously, and we hope to learn from the outcome of today's event. And before we move on, I would like to tender an apology on behalf of the team for not providing the papers ahead of time that we're going to be looking at today. In subsequent meetings, we would make sure they are available for us. And in that line, our approach today would be to have some minute of presentation on the topic we'll be looking at, or on the materials we're reviewing today. We have a 30-minute presentation. And while that is going on, please feel free to put your questions in the chat box, and we will take them down, and the presenter would do well to answer them, and that would also facilitate our discussion going forward. Right now, I'll be introducing our presenter for today. Give me a minute to share my screen. I should have that up. Okay. So this is, we're looking at improving outcome of colorectal cancer using chemoradiation and artificial intelligence. And that will be presented by Mr. Abayomi Opadele. He's from the Department of Proton Beam Oncology, Faculty of Medicine, as the Graduate School of Biomedical Science and Engineering, Hokkaido University. And I believe today this is going to facilitate a lot of discussion in this area, especially in the hot topic, artificial intelligence, and how we can all make use of these opportunities as they afford themselves in the field of medical physics. Right now, I'll be turning over to Mr. Abayomi. Thank you.
Thank you very much, and good day to everybody watching us from all over the world. So I'll start sharing my screen now. Can you all see my screen?
Yep. Okay. Yes.
So, good afternoon once again, and thank you for coming. My name is Emmanuel. The title of my talk is focused on colorectal cancer. I'll be sort of focusing on the two of the strategies for improving the outcomes of CRC, or colorectal cancer as the case may be, by focusing on chemoradiation and artificial intelligence. And a couple of disclosures: all scientific data, except for graphical designs, were actually taken from these two papers, and I take responsibility for the interpretation. So the first paper is from Professor Ruthkam's group at the University Cancer Center Amberg in Germany, and the title of the paper is Radiosensitisation and Enhanced Tumor Growth Delay of Colorectal Cancer Cells by Sustained Treatment with trifluridine and tipiracil and X-rays. And the second paper is from Lin Singh's group, the popular professor at Stanford. I think he's one of the world's most renowned publisher when it comes to artificial intelligence and medical physics. And the title of the paper in GI cancer is Development and Validation of a Model to Predict Survival in CRC using the gradient boosted machine. So I'll be sort of drawing from these two to sort of present an understanding on how CRC can be further treated. So as an introduction to my talk, the three most common ways of treating cancer are radiation therapy, chemo, and surgery, like we all know, and others. And others also sort of account for treatment options like hormonal therapy, targeted therapy, immunotherapy, and etc. And of course, too, we already know that 50% of all cancer patients will receive radiation therapy during the course of the illness. And this is very interesting data that, like you already know. And the next question would be, if 50% of all patients undergo radiation therapy in their lifetime, should we develop a new technology for cancer treatment, or should we just focus on optimizing the efficacy of radiation therapy? And from an economic point of view, you have to look at cost and benefits, right? So because 50% are already used to one treatment option, it will be very, very cost effective for us to improve and optimize the efficacy of radiation therapy. And of course, that is perhaps the basis of all radiation therapy research, or radiation biology research, pardon me. And of course, it is also interesting to know that 63% of all cancer deaths are actually reported to be coming from developing countries. Isn't that interesting? And of course, so let me just sort of begin to spur a conversation just with this data, that if 63% of cancer deaths are reported to be from developing country, then which means that scientists or medical physicists or radiation oncologists from Africa or from developing countries should be the one providing, solution to finding a cure for cancer. And of course, if you look at this map from Cancer Atlas, it basically shows the most common cancer cases in Africa. And as you can actually see, that breast and cervix are quite more prevalent all over the continent. But if you notice very clearly and extensively, you notice that CRC is missing, right? So what's the problem? Don't we have CRC cases in Africa? Or are they underreported? Or perhaps CRC is not common? And that is the reason why I'm focusing on CRC. So why CRC? Before I sort of read the stats from Globocon, the image on the right sort of shows a depiction of the difference between a normal colon cancer, a normal and a colon cancer. And of course, this diagram sort of shows an object-like structure which looks like mushroom. It's called polyp, and it's basically an abnormal tissue growth that lines the wall of the colon. Perhaps it could be located in the ascending colon, the transverse colon, the descending colon, and even to the rectum. So when this basically forms, then of course it's a depiction for colon cancer. So from Globocon now, some of the statistics that have emerged over the couple of years about CRC is that, number one, it's the second most commonly diagnosed cancer in male, following prostate and lung. Third most commonly diagnosed cancer in female, following breast. It ranks for the third cancer-related mortality. It's a multiple organ carcinoma, of course. It's a combination of the colon and the rectum. And again, so 65% of CRC cases are found in developed countries. I mean, that is quite interesting and intriguing to know. And of course, it is less common in women than in men. And screening basically reduces CRC mortality by 60%. And this is my personal opinion. I think that CRC is often taken for granted and therefore goes undetected. Hence the reason why some of the cases, or a larger percentage of the cases, are found in developed countries. And of course, this should sort of begin to sort of incite a thinking pathway as to why this is common in developed countries and why it is often not reported, or why even when they are reported, they are found at very late or advanced stages. So now to the first paper by Professor Rothgans group in Germany. These are some of the problems that I think that they asked before they sort of continued in this research. The first thing was that a particular chemotherapy drug by the name of flurpiridine achieved a failure in a clinical setting, so they needed a review. And they wanted to sort of find out if the combination of trifluridine and tipiracil, which is FTD and TPI, could serve as an adjuvant therapy for CRC patients. And of course, so they also wanted to investigate the radiosensitization effects of this drug. And of course, so they also wanted to know if the combination of chemo and radiation would improve overall survival of CRC. So this is sort of like an overview of the research for those who are very new to radiation biology research, or for those who would love to. So I sort of just designed just to sort of let you know exactly what they did in the research. So they first seeded human CRC cell lines. They treated with tipiracil or trifluridine, and they determined the survivability. Then after that, they combined the treatment options, so that's chemo and radiation together. Then, of course, they sort of looked at the clonogenic survival, which is the ability of cells to survive after treatment. They looked at a couple of dose enhancement factors. Then, of course, so they also sort of evaluated the DNA damage because of the dose response using this marker, and they evaluated the radiosensitization effects. Then next, they also sort of did the flow cytometry to sort of analyze the cell cycle progressions. And of course, so they also did in vivo experiments to evaluate tumor growth. So it's a very simple but very analytical paper that sort of just evaluated ways of improving CRC. And some of you might want to ask, I mean, why CRC? And let me just chip in here. Sort of like a disclaimer. Personally, I do not have experience with CRC, well, because my experience are basically focused on brain cancer cells and breast cancer cells, specifically on GBM, glioblastoma multiforme, because they're the most aggressive form of brain cancer. And breast cancer, of course, they are most prevalent in Africa, as you can see from one of the data. But recently, after the death of Chadwick Boseman, I began to read about CRC, and some of the data I found with I was sort of gobsmacked. I mean, they were intriguing to me. So I thought that it could sort of raise a conversation as to focusing on a cancer that is third most diagnosed in male, and of course ranks for the third cancer-related mortality. And of course, it could sort of pave a way for a new research into cancer treatments in Africa. So in the first figure, they looked at the survivability upon monotreatment with chemo and radiation. And as you can actually see, at different time points, the cell actually basically shows a decrease in survivability after the 2 treatment time points, especially with cell SW48. So look at these cells. We have CACO2, HCC 116, HT29, SW48. So these are the 4 CRC cell lines that they used as a strategy for the study. And as you can actually see that at 2 different time points, you can actually see the decrease in the relative survivability upon different concentrations of the drug. And of course, so if you look at figure C and you look at the surviving fraction, at an increased concentration over a period of time, you can actually see a very low surviving fraction. And of course, too, when exposed to radiation, you can actually see that with an increase in radiation, of course, the surviving fraction declines. So this just basically shows the sensitivity of CRT to either chemo or either to radiation. And of course, too, you can actually see that the survivability will decrease at the exposure to chemo or after exposure to radiation. And of course, so they also sort of looked at the colony formation ability of the CRC cells combined with these 2 treatment options. And of course, these are the time points at 1 hour with radiation and treatment, 6 hours, 3 hours with radiation and 3 hours with the chemo, 6 hours and 24 hours. And if you compare the first treatment time points with the extended treatment time points, you will actually notice that there is a decline, a very sharp decline, as you can actually see in the surviving fraction of the cells compared to just 1 hour treatment, which actually shows that the colony formation ability of CRC to actually survive, okay, is more extended in this treatment time point. And of course, so they also looked at FTD incorporation to sort of monitor cell cycle progression. And as you can actually see, that with an increasing concentration of FTD, which is trifluridine, you can actually see these black patches, which basically shows the incorporation, that's the uptake of the drug into the cell. And with an increasing concentration, you can actually see the increasing spikes, right? Which actually shows that the cells can actually uptake or sort of incorporate this drug more effectively okay? And of course, too, they also looked at the combination over a period of time. And of course, you can actually see the spikes, right? Showing extended period of time, so which shows effective incorporation. So which basically means that when trifluridine or TPI is treated into the cells or into CRC tumors, they can be effectively, taken up by the tumor itself. And of course, they also looked at the fraction of polypoid cells with treatment time. And what is polypoid? Polypoid basically is the ability of a cell to sort of express multiple or binucleated nuclei. And of course, and this basically is a marker for DNA damage response. And of course, as you can actually see that with an extended period of time, there is a sharp increase in polypoid formation after the uptake of this FTD. And they also, of course, look at the EDU incorporation. You can actually see with an increase concentration, there is an increased uptake of the drug into the cell. Basically, it just shows that the cell has good uptake ability for this specific drug. And of course, they also looked at the effects of this drug on gamma H2X induction. Gamma H2X basically is a marker for identifying the DNA damage DNA damage that is probably induced by an internal or an external agent. And of course, this is an immunofluorescence picture. And I must actually, because it, of course, is a journal club, so I must, of course, fault this paper because the image, was not well appreciable enough given the standard of the paper. But of course, as you can actually see, at a very much lower concentration, you could see very little gamma H2X. With an increasing concentration, you can actually see increasing gamma H2X, which actually shows that when the cell is treated with the concentration of FTDI or TPI, there is more damage to the cell. Basically, that's what it means. So which means that it actually causes more damage. And if you look at the fluorescence intensity, with an increased concentration over an increased period of time, you can actually see that the fluorescence intensity increases, which of course correlates with this report. And of course, so they also look at the survival probabilities of the tumor. So for those who are in cancer research, this diagram basically is a Kaplan-Meier curve, which is basically a parametric statistics that is basically used in medicine to sort of estimate the survival of patients over time that were elapsed from a certain treatment. And of course, if I could just explain briefly what this curve basically means. So this is the surviving probability, and this is, of course, the time. Basically, what it means is that you want to know the surviving fraction or the surviving ability of a patient to sort of thrive after being treated with this drug. So this is the control. So this is the drug. So this is radiotherapy alone. This is radiotherapy plus another drug. So this is radiotherapy plus the FTD and the TPI. And as you can actually see, compared to control alone, I mean, very good results. The surviving probability is about this 100%, 75%, 50%, 25%, 0%. And over an extended period of time, we can actually see that cells, okay, that were in the control set alone could only survive up to mid-20 days. But patients, or let me just use patient as the case may be, that were actually treated with radiotherapy and this drug could actually survive for a very period of time, which basically shows the surviving probability of this drug. And of course, so this is for the first cell line. This is the second cell line. You can actually see, compared to control, compared to radiotherapy and the drug and the chemoradiation, you can actually see a very good surviving probability. I'm trying to rush so that we can have time for sort of discussion. And of course, can always feel free to sort of drop a message in the chat box if I'm moving too fast, so I can notice. And of course, too, for other cells, given the variety of radiation change, you can actually see the control compared to radiotherapy and chemoradiation. You can actually see a very good survival probability. So basically, this just shows that the combination of FTDI and radiation shows a very good survival probability for patients that will be treated with this strategy. And of course, so they also looked at the xenografted tumor growth curves. And as this is the tumor volume, and this is the day of the treatment. So this is day 1, this is day 40. This is the control in red. So you can actually see that the control, there is a very sharp increase in the tumor volume. And of course, this is the radiation therapy with chemoradiation. You can actually see a decrease in tumor volume. And of course, for all of the different cell lines, you can see the tumor volume control increase, the tumor volume for combination treatments decrease, which actually shows that this drug and radiation can actually decrease tumor volume, okay, of CRC. And of course, so this is the tumor growth curve. Look at the control. This is radiation therapy with chemo. This is the growth rates for control. This is radiation therapy plus chemo. Basically, it just shows that this is very, very effective for treating CRC. Okay, so I'm going to do an overall summary. So this is the first paper. So the second paper on artificial intelligence, which I really want to sort of talk on, is from a paper by Lensing, and they sort of developed and validated a model to predict, and notice the word predict, and of course, which I think I'm going to sort of raise a conversation on at the end of this. So the model was to predict the survival of colorectal cancer in using a gradient boosted machine. So some of the research problems that they sort of looked at was, number one, CRC survivor were only estimated with nomograms. Nomograms, basically, they are a pictorial representation of a data. And in medicine, they are basically, you just sort of use biological data to sort of depict a statistical prognostic model to generate a clinical event such as the occurrence of deaths, the occurrence of cancer, and blah, 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 like that. So normally CRC survival were only estimated by nomograms, but nomograms, the efficiency of nomograms, you know, are not reliable. So you needed something like an accurate prediction method. And of course, they sort of used AI to combine several features of tumor phenotype, including with the other risk factors or socioeconomic factors that would enhance prediction. And of course, too, they also wanted to look at the model that would offer a personalized medicine, since you're sort of moving towards precision and accuracy in radiation therapy. So the paper, so this is an overview of the research. So what exactly did they do? They sort of looked at the PLCO trial. For those that are in radiotherapy, you already know about the PLCO trial. And basically, it's a trial of about close to 150,000, about 155,000 patients. And between these 155,000 patients, they did a 10 years follow-up. And they realized that about 2,500 patients were diagnosed with CRC. So they divided these sets into two parts, the training sets and the test sets. And basically, this is always the standard in any machine learning or deep learning research. And after this division, then they use the gradient boosting machine technology. Basically, this is just deep learning, which I'm going to explain in the next slide. So basically, what did they do? They sort of use this GBM, which stands for gradient boosting machine, to sort of predict the accuracy of the data that they collected to tell us what will happen to you, or the risk of dying within a specific period of time after CRC diagnosis. So basically, they use an XGB booster Python package to be able to sort of create this model. And one thing I love about this paper was that in order to make the model more interpretable, then they converted it to a web-line based model, whereby you can be able to just input your data, and of course you can actually see it on the website, which I'm going to explain. So that's the overview of the research. So what's artificial intelligence? Basically, it's just developing a program that can help humans to reason, or that can help data to sort of think like humans. And of course, it consists of ML and deep learning. And basically, how does it work? You have a raw data, okay, you analyze the data, you extract the data, you train the data, which any of the algorithm you want to do, then you evaluate the data to give you a result. And one thing about AI model, as in comparison with any statistical model, is that it has a scalability of performance. Increasing data, of course, leads to increasing performance, which makes it very different from every form of statistical modeling. So what is the gradient boosting? So the gradient boosting basically is a machine learning technique, very simple technique that basically is used for analysis of regression, classification, and sort of understand a whole lot of problems. And the gradient boosting basically is just to predict a model, okay, using decision tree analysis. And like I said in the previous slide, they sort of use a Python package for this, the XGB boosted Python package, I believe, which has a very high performance. So this is the data. They train the data to give a model, they retest, they train, they retest, they train. So the data can actually predict. So basically that's what the gradient boosting machine model is all about. So it's training the data will recognize a specific set of data. There are a lot of iterations. Then of course, then the data can be used for prediction. So the data in the research, I thought of showing you some of the characteristics of patients with CRC in the PLCO trial. And I wanted to sort of point your attention to this. Remember I told you that they got a total number of about 2,500 patients that were diagnosed with CRC, right? So it is very interesting to note that out of those 2,500, only about 10%, okay, had undergone radiotherapy. And of course, too, I think that does not correlate with the global statistics that says that 50% of all patients will undergo radiotherapy in their lifetime. So the question is, why is it that a very small amount of people that are diagnosed with CRC actually undergo radiotherapy? A typical guess could be that maybe I will leave it for the discussion, but in my thinking, I think it would be that most people are sort of diagnosed at a very advanced stage. So basically, this is just for palliative, I think. And of course, it's very interesting to note for anyone that wants to pick something like this up for research. So, so after the data, they sort of did the metric performance evaluation. The accuracy was 83%, the precision was 67%, the recall was 85%, the F1 score was 75%, the area under curve and the ROC was 84%, which shows a very good accuracy performance for the data. And of course, they also did the performance model curve to sort of show the probability of death from CRC within 10 years as calculated from the Python package. So this dotted line is the perfectly calibrated curve. And this is the SG boosted curve. You can actually see that the SG boosted curve perfectly sort of correlates with the calibrated curve, which shows that the model that the sort of develop has a very good prediction accuracy. And again, so they also use the Shapley value to sort of pick relevant features that could sort of predict the risk to die within 10 years after CRC diagnosis. And sort of just maybe to tantalize you a little bit, in my imagination, I would have thought that some of the features to predict would be related to the tumor phenotype. But unfortunately, no. So if you look at this data, very interesting. They actually saw that from the Shapley value, this is the indicator. Red shows very high, blue shows very low. So look at work activity, history of cholesterol, income. I mean, which means that activity, cholesterol, you know, the rate of income that you have could actually be a very significant factor to sort of predict the risk to die, you know, from CRC diagnosis, as compared to perhaps the stage of the cancer, as compared to the histology. I mean, which is sort of interesting. And of course, too, if you look at this, it kind of correlates with the former data I presented, whereby 65% of all CRC cases are from developed nations. And of course, if you look at the income, that study sort of correlates together. And of course, too, after the developed model, remember I told you that in this paper, to make the model more interpretable, they sort of used a web-based analysis to save the file, then transport some of the files online such that a virtual patient can just click on the questions and see the responses as the case may be. So I'm going to show that in the next slide. So I'm going to put this link just immediately after the presentation. And basically what it did was that after all of the training, after all of the model, after all of the artificial intelligence jargon, then you can go to these websites, and of course it shows you how to input your own data by yourself. And of course they sort of divided the questions into 32 specific questions. So you insert or you just answer as the case may be. Then when you answer, it's going to give you a predicted value. And of course, I try to sort of do the virtual test by myself, selecting the worst possible options. And of course, you can actually see that if the virtual patient has been diagnosed with CRC, this model could actually predict that that cancer patient would die from CRC, okay, within 10 years by a 75% probability, which shows a very good accuracy of the prediction. So the overall conclusions and key points. So what exactly have I been trying to say since morning? Number one is that a daily fractionated combined regimen of trifluridine and tipiracil in combination with radiation improves the outcome of CRC. Screening tests for early diagnosis contributes to an increase in survival rates. Okay, and of course, too, the drug shows clinical relevance activity after pyrimidine failure. This perhaps might be very useful for medical physicists that are working in radiotherapy facilities who might be interested in doing the radiobiology research. And of course, today I was used to provide an accurate prediction of survival in CRC using several features. And the AI could also be used as a personalized treatment. And what are some of the research insights? Because this is actually the reason for the journal club. So while reading the paper, these are some of the things that I think that we could pick from this and we could sort of adopt into our own research. Number one is that there is no sufficient data on CRC post-radiation treatment in Nigeria and Africa. For example, I was trying to look at are there any data that sort of speaks on, the surviving probability of patients that have undergone, a specific form of cancer treatment in Africa and Nigeria? I couldn't find a very exciting data. And of course, this could be something that one could explore. And of course, to remember that they use FTDI and TPI, and of course, the very good research on understanding radioprotectors, radio enhancers, and radiosensitizing agents. So I think we should also begin to, beyond radiation, beyond treatment planning, we should also begin to look at putting our hands to do laboratory work by sort of developing radioprotectors, that could sort of protect radiation damage, or that could definitely enhance, radiosensitivity effects. And of course, very important, I also noticed that there are reduced clinical papers, especially from a medical point of view. If you go to Lancet, or if you go into Science Nature, if you go to any medical paper in the world, you discover that most of the clinical papers, and with respect, are from clinicians, are from oncologists, but very few clinical papers are from medical physics standpoint. So for example, I was trying to check, do we have a paper that sort of looks at a concentrated evaluation of DVH for glioblastoma multiforme, which is the aggressive form of breast cancer, spanning a decade in Nigerian cancer patients? So if you have a data like this, it will sort of give us an understanding on to better how to treat GBMs, how to provide a solution for GBM treatment or any other form of treatment. So medical physicists need to churn out clinical data from their workplace. And I think that this is something that one could explore. And of course, we already know, there's a significant dearth of computational modeling studies in Nigeria. And let me just pause on this a little bit and say that one thing I've noticed is that, and of course, as can bear witness with me, if you go to Europe, America, Canada, or come to Asia, I mean, there are a whole lot of experimentalists, people working with high novel equipment, okay, trying to churn out research. But you will actually notice that what makes the research novel is the combination of experimentation, right, with computation. And it's very often difficult to combine these two strategies together. But when you combine them together, the paper becomes novel. But when you flip it over to Africa, we don't have enough equipment as much as we should. So we should sort of take advantage of using computational models, just on your computer, and sort of explore, and play with data and be able to create, a novel idea. And lastly, I also think that there are more papers on prediction studies, just like this paper. People are predicting the risks to die from cancer, the risks to die from tobacco, the risks to die from radiation, but there are less people on detection technology, and I think that is where the future is. So we need to move from prediction to actually, detecting specifically. And of course, these are some of the insights that I think that we could gain and we could adopt. I believe this is the conclusion of the paper, and it's a quote, popular quote that says that research is not for the purpose of acquiring a degree, rather it's for the purpose of solving a problem. So if we can see a problem, let's try to conduct the research instead of waiting to get admitted into a degree for the purpose of conducting research. Rather, research should be for the purpose of solving a problem. Thank you very much for your attention. I'll be glad to have your questions, comments, and thoughts. Thank you.
Thank you very much, Mr. Abayomi. And I hope the audience and everyone participating are able to pick one or two things from the presentation and are steered up in line with research. And you must have a lot of questions. I have a couple of them myself, and this is the time for us to ask questions. And feel free to also type your question in the chat box. You can unmute when you have a question, and I believe the presenter and anyone can also pick on the questions if you have answers to them. Thank you.
So thank you very much. So if you have any questions, kindly let me know.
Okay.
Might not be related to the paper, if maybe anything on how best we can improve.
Hello, can you hear me?
Yeah.
Yes.
Hello. Okay. Thank you, Mr. Abayomi, for the presentation. I was just listening attentively, trying to learn and take in as much as you were saying. But I just want to point out something. I think we can also discuss, not only, I don't have a question per se, but I just want to raise a discussion. From your last, is it the last slide now, or the last but one slide, where you were talking about how we can come in, as Africans, Nigerians, from my own point of view. You made mention of how most of the papers you find online are from oncologists and very few are from the medical physics. And you also pointed out how that medical physics can carry out retrospective studies, from DVH. But I just wanted to say, at least from my own point of view, from Nigeria, as a clinical physicist, we have about 9 radiotherapy centers, and probably in a year, you have maybe just 1 or 2 of them working. So, and even amongst the 9 radiotherapy centers, let's say about 20% of them use treatment planning systems for external beam radiotherapy. I don't know, can you hear me?
I can hear you.
Yes, so I'm just trying to make a point that, data really is the major challenge. Sometimes you have an idea, you want to carry out a study, you cannot find the data. Either retrospective studies or prospective studies, data is a major challenge. So how can, going forward now, this is 2020, we don't have data. We don't have DVH, or I doubt if you can even have DVH of 10 years. I am not sure any center can. I'm not speaking authoritatively, but I don't know if you can produce that. And some of these studies, you need something as far back as 20 years if you want to get meaningful results, that can make good predictions. So how can we work around that now going forward? Because as medical physicists, here it's very difficult. You are not really the one in in of the patient. So even when you want to do prospective study, there are so many bureaucracies surrounding all the rest. So I mean, I don't know. That's personally my own interest with the challenges we have now. What can we do? What can we do? Yeah. Not for you alone, for everyone. I would like us to discuss that. Yes.
I mean,
Thank you.
It's an open discussion. So if anyone have a thought, please, you could unmute and let us know. I think from a point, it's a very interesting point to know. One of the ways of going forward, number one, is to maybe look beyond clinical data. I understand that radiotherapy machines are sort of working epileptically over the year, and which might inhibit patients coming for treatment. So I think going forward, we should look beyond clinical data as regards to getting data from patient treatment. And of course, we can now transmodify or transmorph into getting data that are related with the physical maintenance or data related with engineering or data related with just what's the right word? Just data that are not necessarily acquired from, that are not generated, from the patient. So you could just basically look at, maybe just pick up your computer and sort of look at maybe beam accusations and sort of just do data that are maybe physically generated instead of patiently generated. So I think going forward, maybe that could be some sort of options. And something just came to my mind. For example, we have an abandoned radiation.
I was going to step in a little bit from there. I want us to keep questions to within certain minutes so we can take other questions as well.
Okay.
Yeah, so going forward, I would want to offer that for questions, please let's keep it within a minute, and hopefully we can have more questions. And for questions that are not thoroughly attended to, if there are still enough time, then we can come back and pick that up. Thank you very much. I have a hand up by Mr. Mack. Can you go ahead and ask your question, please? Feel free, whatever method, whether you want to type it in the chat box or ask directly. Thank you.
All right, thank you. Good evening. Good evening, everyone. Thank you, Yomi, for the beautiful presentation. AI and indeed artificial intelligence is also one of my areas of interest, and I always look forward to listening to Nigerians and Africans discuss topics relating to AI. I'm in line with what the last speaker said about the challenges we have in Africa, specifically as it relates to data. Yes, I know even when we talk about clinical data, it goes beyond just having those data. Another problem you have is the quality of the data. Because if your data is not of high quality that you can actually use to train your models, then that data is as good as useless to you. So we have that issue with even acquiring quality data. However, my problem is even when we are able to access data that are in database, online data repositories and the rest, we have another challenge of knowledge gap when it comes to hands-on experience with artificial intelligence programming. So I would like Yomi and probably others to comment as to how can we bridge this gap, because as a physicist who studied in Nigeria, sincerely, the level of computational studies and courses we took is almost nothing to write home about. I don't know if it's the same in other African countries. So when you want to now do advanced studies and you have to work with some of these programs, it becomes very difficult because you have to learn all over again. So I just want to ask, since we have a few people who have probably overcome that hurdle, can you share your experiences as to how you were able to cope with this deficiency and how you overcame this hurdle? Thanks.
Very nice comment. And the personal experience for me was that I didn't have sufficient knowledge of what artificial intelligence entailed about a couple of years ago. But perhaps what prompted my interest was a pressure to perhaps engage in research when I saw my colleagues doing the same. So pressure from colleagues sort of gave me the opportunity. But specifically, one thing I've noticed, especially among my colleagues, African colleagues, is that we want to sort of use AI or any form of computational package for research. So we sort of download all of these things, you know, okay, maybe I'm going to pick Gen 4 today, I'm going to pick R tomorrow, I'm going to pick C++ tomorrow, I'm going to do this and that. And I noticed that over time doesn't work because we have a lot of other life activities. So basically, this is the way to go. Pick up a research or maybe a problem. Okay, I want to solve this particular problem. And what is the best computational tool to solve this problem? Just one computational tool. Maybe as I digress, the essence is not, you know, the important thing is not basically using, you know, a statistical package for your research. It's just basically, you know, solving a problem. So you don't have to really focus on which to use. So you just have to design a problem in your mind. Then after you design the problem, then you look out which computational model or which programming language would help you to sort of train that data. Then once you do that and you just pick one, for example, I'm using Gen 4. So Gen 4 basically is a radiobiological package data that basically helps to understand interaction of radiation with matter and with DNA. So I just sit down and just look at it, and every day I keep on trying. Every day you keep on trying. Rome was not built in a day, and you become proficient on it every day. So just pick one, try every day, ask yourself some questions, try to answer them by yourselves. Then over time, I mean, you just get used to it. And let me put it in this very simple way. Nobody taught you how to use a phone. Nobody taught you how to use a computer. You just opened it one day and you started using it. So same thing again for anything related to programming or anything related to any computational modeling. Just download it, pick it up in a day. There are a lot of resources online. Start using it by yourself. And I mean, you'll be surprised at how far you've gone when you begin to do this by yourself. Yeah.
Thank you, Mr. Abayomi. And thank you for the question, Mr. Mark. Just a quick comment. Speaking about data in terms of the quality of the data and gathering data, I would just speak in this light that if we as a people encourage research culture, that would help in the clinic itself. So because the research is not just medical physics related, we work within a team. And as a team, we have the radiation oncologist, the dosimetrist, and everyone working together. If a department have a research culture, then we would know why we need to keep some materials in line with what we want to investigate. But if it's the quest of the medical physicist alone to kind of try to check what's the outcome of this technique I'm trying and the likes, that may become difficult because you would need to bring every other person on board. So I think a good way to encourage data sharing or data gathering and keeping, I know most systems will have a record and verifying system or all those other things that are used to keep patient records and the likes. So I feel if a department, not just the medical physicists working alone now, embrace a research culture, and this can everyone can bring this up at their own meeting. If you're working, that's, I'm assuming, I'm just speaking in terms of clinical practice. And if one is in a school program like myself, of course there are many research lines around that one can opt into. That's just another a quick way to think about that. I have a question related to the machine learning aspect, and also if anyone have question, please feel free to type it in the chat box, or just you can also give an indication that you have a question by raising your hand, and I'll call on you. Thank you. My question is related to machine learning and the specific endpoint that was chosen for the paper you talked about, which is the last part. I realize for every prediction you make, you're going to have a different result depending on your endpoint. And I am curious to know how the predictors, how they propagate to that endpoint. How do they relate directly to the endpoint? Because the endpoint here is about survival, whether the patient is able to survive after 10 years or something. So how do they directly relate? Because some of the factors look ambiguous. That's what I was thinking about.
Okay, I mean, very, very interesting question. And I think that was sort of what also prompted me to look at the research. Speaking of endpoints, there are several factors or several risk factors for cancer. And in the back of our mind, I mean, in the back of our mind, without any educational knowledge, we'd often think that most risk factors are genetically generated. For example, if you sort of want to look at, for example, let's say breast cancer, you maybe want to look at family history, or basically you want to look at maybe exposure to carcinogenic materials, as the case may be. So we often think that some of these factors are just basically clinically generated, as the case may be. But in this research, they sort of looked at a wide range of endpoints. And if you recall, I mentioned something which is nomogram. Basically, to predict survivor, the gold standard of predicting survivor for CRC is nomogram. So nomogram basically works such that you pick up, the tumor characteristics, such as the grade, the stage, the volume, the size. So everything is all about the tumor. But they actually exclude the patient's lifestyle. So I think this research sort of just combined, all of those factors together, including the tumor itself and outside of the tumor. So biological factors, and of course, socioeconomic factors, and all of the factors. And the beautiful thing about models like this is because they are trained. And when they are trained, you can actually see the metric performance. So when you combine all these factors together, even though some of them might be ambiguous, as the case may be, once they are trained, you can actually see the metric performance. And if the area on the, if the RUC, which is the area on that curve, is sort of above a certain, above, let's say about 0.5, then it shows that the data is actually trainable. So it's about training the data, is about sort of combining factors together, it's about retraining and retraining, and that's why it's a model. So I don't know if I sort of answered your question.
Sure, thank you. The ROC curve, though, sometimes also depend on the predictors themselves, because you are technically plotting a graph of specificity with sensitivity. And in that case, depending on what you have defined to be your marker, that can flip things. You can have something showing up down in the graph, and maybe you could have classified them differently. My comment in that line is just related to machine learning, how it's still subject to the person's performing the study one, and also the limitation of the algorithm itself. For instance, the gradient boost algorithm that was used, has its own limitation for in terms of computational powers and the likes. Okay, thank you. We have about 3 more minutes to wrap up these sections. This section. Do we have any other question?
Just the comments to what you raised. One of the challenge that is ravaging artificial intelligence study is that if you look at the study itself, and you mentioned it, we just have the results. But what about the codes? What about the algorithm that was developed? I mean, people don't share the data. So replicability is an issue, and that is one of the challenge. So we don't know whether some are just sort of, personally modulated, as the case may be, or maybe how can, somebody in Congo, Africa, replicate this study on their own and try to develop the same. So we don't know if there are a couple of challenges that are related with this study, as the case may be. And I think that's the challenge of any AI data. If you look at any AI paper all over the world, especially from some very few where they actually publicly share their code, it's very, very difficult to sort of replicate this study. So I think going forward as African researchers, when you sort of engage in any model training data, then the ability to sort of share your data online gives credence to the replicability of the data. So
Thank you.
This is what Africans should look out for.
Thank you very much. I have just a minute left, and I'm seeing a hand by Mr. Mac. Kindly talk to us in 30 seconds. Can you do that, please?
Just okay, so seconds. I just wanted to back up. Luckily, Yomi actually made a lot of the points I was going to make. So one of the challenges we have with the AI technology is that for now, it's still a black box technology, which means we see the results, we see the problem, but what happens in between is still very unclear. So we would solve that problem at some point along the line. However, I would also like to suggest that one of the ways we could develop ourselves as African scientists and medical physicists in particular is by coming together and forming research groups within our localities such that we can share knowledge, especially in the areas of AI. And then, as Yomi has said, we should also post our codes online. Of recent, you can actually go to GitHub and you will find a few codes. They are still very few, but I believe with time they will always increase. Thank you.
Thank you very much, Mr. Mac. And that marks the end of today's journal meeting. This is our first of many to come, and we believe it's been at least impactful. We would, like I offered an apology to start with, that we sincerely apologize for not sharing the paper ahead of time, and in subsequent journal club meetings, we hope participants will have the paper ahead of time. And okay, I'm just receiving a message that the video will also be posted to YouTube, so we can take a look at it one more time. All right. Would also appreciate any feedback, any comment, any suggestion on how better to do this going forward. Thank you very much. Okay, I think one more thing that I'll have to mention to complete my job here is that the next meeting will be in the next 2 weeks. It will be in 2 weeks' time. And ahead of time, once again, we promise you're going to have the paper and to help us build on the discussion. Once again, my sincere appreciation goes to Mr. Abayomi for the wonderful presentation, walking us through and raising the discussion. Thank you very much. All right.